go ahead and get started. Welcome to the exida presentation of Determining SIF Response Time. Little bit of information for moving us forward. Audio is being provided via the internet, so make sure your speakers are enabled in all places, and please keep your microphones muted. There is a question and answer tab at the top of your screen. Use that mechanism if you have any questions at any time. I will answer them as we progress through, and we'll also have a Q&A session at the end. We are doing a recording of this session, and a copy of the slides and the audio presentation will be available to you, posted on the website. My name is Denise Chastain Knight. I am a chemical engineer and a senior functional safety engineer for exida. I have more than 30 years experience working both in industry and in consulting through design activities and in process safety instrumentation. I've been fortunate to have exposure to a number of different industries, chemicals, polymers, pharmaceuticals, petroleum, power industry, and applying functional safety in many of those areas. I'm the representative for exida to the Center for Chemical Process Safety Technical Steering Committee, and also a past chair of the Chemical Exam Development Committee for NCES. We actually developed the materials for the PE exam, and I'm still a current member and a fellow of AICHE. exida has a number of offices located worldwide. We're fortunate to be able to serve our customers in their neighborhood and be exposed to numerous parts of the world and how industry operates there and the application of functional safety in these other locations. exida is involved with the complete supply chain of functional safety in multiple industry sectors, from original equipment manufacturers who require product certification through to the end users that use the products. exida provides software, tools, training, consulting, and procedures related to functional safety, security, and reliability. The main products and service categories for exida include consulting in the functional safety area, alarm management, and control system security. We develop and produce engineering tools such as our Excellentia suite of products that carries the functional safety life cycle from hazards assessment through cell verification. We also have tools like Cell Alarm for alarm management, CillStat, Cyber, PHAX tools, and then the Safety Case and FMEDA tools for analysis. exida provides product certification in the functional safety and cybersecurity arenas, as well as training in all of these areas, both standard courses that are often as open courses, but we are also happy to do custom courses for any of these focus areas on-site or off-site for individual users. There are many of reference materials available, the databases that accompany the different engineering tools, as well as textbooks and reference books. And then exida also handles professional certification for individuals, CFSE and CFSP, with a number of different categories or areas of focus for that certification. exida certification, the tools that we use for doing device certification, looks at systems, products, components, and in personnel, looks at both random and systematic failures, and can also look at certification from a system standpoint, such as for cybersecurity and network robustness. And this slide shows you some covers of some of the materials that are available through exida, the books. There's extremely comprehensive handbooks on equipment failure and on techniques for functional safety, available via exida at our website, exida.com. The engineering tools, here's a little more detailed look at the content of some of those tools. The Excellentia suite of software, Cell Alarm for doing alarm rationalizations and alarm management, and then the CillStat tool for collecting field data analysis, as well as the Cyber PHAX for cyber risk assessments. Our topic today is determining SIF response time. So we're going to start by looking at the basics of what's required for SIF response time, some background. What do the standards say to give us guidance on what's expected? With this being a time element, we're going to look at several different things around timelines, how we're going to define the definitions, and then how we're going to break an event scenario into the components so that we can ultimately determine what the SIF response time needs to be for a given scenario. And then we'll have some parting thoughts on how to take this and move it forward into your applications. Some basic definitions. These acronyms will be used throughout the course of the presentation, and I will define them as we go along. For a safety instrumented function, we need to recall that the main purpose of a safety instrumented function is to detect a process deviation, to diagnose what needs to transpire in the form of our logic, and then to take steps to achieve a safe state for the process, our final elements. This is kind of analogous to what an operator does with an alarm when they determine what to act, but with a safety instrumented function, all of this is predefined for the SIF to ultimately respond against a process deviation to render a safe state. One of the requirements we have for functional safety is to develop a safety requirement specification, and within that, defining the SIF response time is part of it. Now, the language that you see at the moment is something that's basic language, but it's really directed towards the different subsystems of a safety function. It's good basic language to be a part of your SRS, but it does not complete the definition of SIF response time. The one area where folks most often struggle and is a little harder to define is what is the response time of the complete function. There may be occasions when a function has to in order to render a safe state within the time frame necessary, has to act much more quickly than maybe some of the individual components. So we want to make sure that the whole SIF is responding in a timeline that is appropriate. Even though we've defined design specifications for individual components, they don't necessarily sum up to the overall time. IEC 61508 defines timing requirements, SIF response time performance, is that necessary for the safety function to be completed. IEC 61511 or ISA 84 takes that a little further in that it brings in this requirement that the SIS bring the process to a safe state. So we've introduced the concept of needing to achieve a safe state as part of that function. As we're defining it, we look at these two to get the clues and realize that the SIF response time is indirectly defined in terms of our process safety time, because it's necessary for the function to be complete and to render a safe state. So the first thing we need to do is look at our process safety time. IEC 61508-4 actually includes a definition for the process safety state. I'm going to actually read it to you. The period of time between a failure that has the potential to give rise to a hazardous event occurring in the equipment under control or the equipment under control subsystem, and the time by which the action has to be completed in the equipment under control to prevent the hazardous event from occurring. So adding this piece of information to what we know thus far, we would define the process safety time as beginning at the initiating event and ending at the realization of consequence. Looking at that from an event scenario perspective, we remind ourselves that the purpose of the SIF is to provide protection against a very specific event scenario. So it is possible to look at the timeline of that scenario and the events and sub-events that occur as that scenario is advancing. Our SIF has to be designed to detect the cause of that scenario, and it must be designed to act in a way that is going to achieve the safe state for the scenario. And of course, when we've defined a SIF, we have set its safety integrity level target considering independent protection layers. But when we're calculating the SIF response time, we do not necessarily consider those protection layers as part of that calculation. Let's look at how we might dissect this scenario to look at the different components of the timeline. Certain independent protection layers are more mitigative. In essence, they mitigate the consequence after the incident has occurred. Our goal of the safety instrumented function is to prevent this incident from occurring, so effectively we are going to ignore any of these mitigative events in this particular time analysis. The scenario will begin, per our definition, when the initiating event causes the loss of control. If you wish to be a little more conservative, you can say the cause is actually when you move outside the process control boundaries, which would bump it up just a little bit and shorten your overall process safety time calculation. Not considered the part that would normally be in control. That's basically a judgment choice as to where you begin that start, but it should be no higher than the top of that process control band. We're going to ignore any operator action in this scenario because basically once the theory is once the event starts to propagate, if the operator is not successful, we're not going to take any credit for any delay they may have built into the system. We're just going to assume there is no, the operator intervention is in no way affected the scenario model that we're looking at. The SIF must trip before, it must respond before the event actually occurs, and we want it to respond early enough that any process lags can be considered, and we can in essence take the process excursion, stop the forward sequence of events, and return the process back into a normal control conditions or a safe state. And then of course the other piece that we're looking at, the other boundary, is the event does occur, and this would be the end of our process safety time, which is the broadest range we're looking for. So the process safety time begins at the initiating event and it ends at the realization of consequence. So we can see a boundary here that we've defined as the process safety time. And as I mentioned, you can take that lower bound and bump it up to the top of your process control region if you want to be a little more conservative in setting this definition. The SIF response time begins at the trip and ends well before the process safety time. So it starts at the trip. You want it to end well before the process safety time so we can give times for the dynamics of the process to move forward. But we need to anchor this somehow. So, looking at how we would break the different pieces of the overall timeline down, process safety time from the initiating event to the incident needs to be well understood, may need to be modeled. This may be a very difficult item to model because you have to require a firm understanding of the process, an understanding of the dynamics. There's engineering judgment involved to look at the rate of which steps may occur along the escalation of the scenario. So you definitely need to involve process engineers in this. It may take some sophisticated modeling tools such as Aspen in order to calculate the process safety time. It may be necessary to do, in the case of runaway reactions, do calorimeter modeling in VSP or RSST or ARC type testing, or to do blast calculation modeling if it's something like a combustible dust that we're concerned about. So quite a bit needs to necessarily go into determining this process safety time and looking at what is the rate of propagation of the incident. The SIF demand, we are going to assume that all other IPLs fail to respond, so we don't consider those timings there. Then we're also going to look at the SIF trip point as a beginning of that SIF response time. And then, of course, our end of the SIF response time is how quickly we want it to respond in order to achieve the safe state and turn around the escalation of the process. One big part is to consider is the process lag. If the response is something like turning off a valve and flow immediately stops, then the process lag may be almost zero. But if it is, for example, a chemical reaction where we're introducing a quench material, we have to allow time for mixing, we have to allow time for the binder reactions to occur to quench that overall runaway reaction, then there might be a pretty significant process lag in that. We also want to include a safety margin. Because this is an engineering judgment and a calculation, there is no one perfect answer for the timeline assessment. So it is good to include some kind of safety margin, and that is a judgment call. And then, of course, we then calculate the SIF response time simply by eliminating all those other values that we can determine. Looking at it graphically, our process normally will operate in a normal operating envelope in control. But when we might call on a SIF, we have a process deviation that is going to deviate away from that normal operating control and actually run into, in this case, an overrun type situation. And what we want our SIF to do is trip in such a way that it can turn that process down, come to the right-hand side of the red piece of the graphic, and bring the process back into control or into a safe state. If the SIF fails or we haven't designed it appropriately, then we may have a consequence. So when we did our definition of, when we're looking at this situation happening, in this particular case we have a very linear process where we can look at a rate of change in our process variable and define the rate at which this event is propagating. And then we can define the process safety time by a simple calculation from the start point to the end point and determine the time based on that rate of change. We know that our SIF response time is here somewhere in the middle, starting at that SIF trip point and ending at the point where the SIF is finished acting and it's started to change what's happening in the process variable and bring the process back to a safe state. Looking at this on just a little bit larger graphic, we'll put those two times back up there. One thing we can easily calculate is how long it took to get to the trip. What part of that process safety time is consumed by the event escalating up to the point where we actually choose to trip it. So we can calculate that number, the time to trip, and again, it's a straight rate of change between 2 points along the modeled curve for the process. And then on the back end, after the SIF has completed its activity, we have some period of time that needs to represent the process response to the event, how long it takes the process to respond and start turning back to the normal process operating range. And then we have our safety margin associated with it. And of course, the calculation for this, the SIF response time, is determined simply by taking that overall process safety time, subtracting out that time to trip, and then subtracting out our combined process response and safety margin time. Just basic math. But looking at that from an example standpoint, in this particular example calculation, we have a storage or tank that we want to hold at a constant, maintain a constant operating level, little red line there in the middle of the tank. We manage this because the process downstream is controlling the pump in order to take outflow from this tank. And then we have a level control valve there on the far left, the one that's not connected to anything. I've not shown any of the basic process control details in this graphic, but it's that far left one that controls the inlet valve. So we have a process control system that is basically independently measuring the level in this tank and controlling that valve. Normal control on this tank is going to be at 50-meter height. It's a very tall tank. And our initiating event will be the failure of the control valve that is regulating the flow in. For this particular scenario, we're worried about high flow, so we're going to assume that fails a full open. Therefore, we're feeding material into the tank faster than it can exit the tank. The rate of change, the maximum rate of change for this condition would be 0.5 meters per minute. That is taking into account the expected range of downstream outflows in order to get us a maximum rate of change or a conservative number. And then, of course, our definition of the SIF safe state is to prevent the overflow at the 100-meter level. And our trip point is going to be at 90 meters. In the example calculation here, we have our normal operating level, which I'm going to indicate, the basic process control level, which would be your normal process operating range, and could conceivably, if we wanted to be conservative, be our starting point, but we're going to use normal control for this example. The operator alarm, and then, of course, the safety instrumented function itself. For the purpose of the calculation, our inlet valve is our source of failure. Our dike is a mitigative. It's managing the consequence. It's not preventing the trip. And we're going to look at the BPCS control and the operator alarm as no, we're not going to consider them. Obviously, our BPCS control was part of our failure initiating scenario, or scenario initiator, and then the operator alarm is going to be considered an unsuccessful IPL, and we will not consider it as part of this calculation. So our process safety time, we're going to define it from the normal operating level to the overflow. Our time to trip is going to be from that normal operating level up to the trip point, our high level of 90 meters. And then the balance of that is our SIF response time, the process response time, and the process safety time, or our safety margin time. So the process safety time is the difference between the overflow level of 100 meters and the normal operating level of 50 meters times our 0.5 meter per minute maximum rate of change, or 100 minutes is that overall process safety time. The trip is at 90 meters, so our time to trip is 90 meters minus the 50 meter normal operating level, again multiplied times our rate of change to deliver 80 minutes on the time to trip. In this case, it is simply turning off the flow valve, which we are going to say is essentially a process response time of 0, that it's almost an instantaneous valve closure. And the site has determined that they want a minimum of a 10-minute safety margin on this particular scenario. So there was a judgment decision made in what that safety margin ought to be. So we take all of these numbers and just plug them into our calculation to get the overall process safety time of 100 minutes minus our time to trip of 80 minutes, less the 10 minutes for the safety margin and the 0 for the process response time, giving us a total safety response time, or SIF response time, of 10 minutes for this particular scenario. Obviously, this example is it's illustrative. It's very slow acting. There's a lot of time in this process, but that's not always the case in the process. So it is important to go ahead and calculate this out because there's not always this kind of a margin. Looking at that from an alternate timeline, what if we do have a more energetic process where the rate of change is much faster, or the process response time is much slower? So this graphic's going to show us that perspective on it. So the process safety time is basically calculated the same way. It is that difference between the excursion or if you choose the normal operating envelope, upper bound of that, and then the consequence threshold. Our process safety margin in this case, it's slower to turn this around. We need either more safety margin or our process is slower to respond. So we need to leave a lot more time at that top end after the SIF has done its job in order for the process to mix and respond to what it's been instructed to do. If we're closing valves here or feeding in a quench material, this would be the time in which it's mixing or reacting in order to bring the process back into control. And so in this case, what we may do is move our SIF trip point much farther down. And this is an important part when you're developing your safety requirement specification. This is a good way to test, are those trip points, do they make a lot of sense? Because in this case, what we've done is pulled that trip point much closer to the normal operating envelope in order to give the SIF time to respond and to give the process time to respond to the outcome of the SIF. So that leaves us a pretty narrow time frame there, a much shorter time in this case for the SIF to respond. So we've kind of backed at this from both directions. So some summary thoughts here. Obviously, process knowledge, engineering judgment is a big piece of making this a realistic calculation. It does require involvement of the process engineers. It may require some sophisticated tools in order to understand and develop those curves that are the basis for what is occurring dynamically within the process during the event scenario, and it is based on a very specific event scenario. The process safety time can be very short, especially if you're talking fire, explosion, runaway reaction, or a toxic release. It may be near instantaneous. So there may be more judgment time involved in those situations, or more engineering judgment and less rigorous calculation in order to make that determination. But even if the numbers are determined from an engineering judgment perspective, they need to be based on what is occurring in the process and the process dynamics. In these examples that we did here in this session, the rate of change was linear, but in the real world it is not always linear. You must understand the process dynamics. In something like a runaway reaction, the timeline can actually accelerate in an exponential manner. So you have to work off of full information, because just taking the very beginning rate of change could very seriously underrate the process safety time or under-calculate it as the process excursion rate escalates towards the end. When we're looking at the process response time or the SIF response time, we have to consider all of the physical, kinetic, chemical, thermodynamic responses of the process. Some of these things can be fairly slow, some of them can be fairly quickly, or happen quickly. We need to look at those in determining that tail end piece after the SIF has finished its task until we actually turn the process around and have achieved that safe state. Have to consider that lag. It can be very significant. And then, of course, the analysis must be balanced. I mentioned a couple times that instead of picking your base process safety time from the excursion, you could take it from the top of your normal operating envelope. If that's the case, you want your time to trip to be from that normal operating envelope as well. So when we apply the analysis, we want to be consistent in where we put the conservative in, not double dip for that, and apply our safety factors uniformly. So that is what I had. Let's look to the questions, and I certainly encourage anybody who hasn't put in any questions, please do so. Let's see, I assume we should consider the time, T90 time of the thermal wells within the total SIF response time, isn't it? Yes, if you have any kind of delays with your process signals, whether it be the rate, like if you're doing some kind of analytical signal, there may be a little bit of a lag while the analysis is occurring, or there may be a cycling delay in a polling delay, polling time associated with that input sensor. If that's something that is significant, then we should always consider those part of the just getting to the time to trip. You've got to take those delays into account, and that may be an additional factor that you need to consider in to adjust that safety response time. Just add another variable to that equation to take into account that additional delay. If you've got any kind of trip delays or lags, they also need to be considered in part of that. Delays within the SIF itself need to fit into that SIF response time. Delays in the process initiating or following need to be considered outside that SIF response time. I don't see any more questions up, but we had one question this morning. Does Excellentia calculate safety or SIF response time? And the answer to that question was no. It really does depend upon the process, and it was so you need other tools that are looking at the process and that intimate knowledge of the process to really calculate that process safety time and thus back into your SIF response time. We have another question. What about the old rule of thumb that SIF response time should be 1/2 of the process safety time? That is a rule of thumb that has been used, and certainly in those cases where you're talking a fire or explosion or runaway, something that's very fast, using that half rule of thumb is a place to start. However, you saw from the dynamics that I put together just in these couple charts that that is not necessarily true, depending on the dynamics of your process. Sometimes your SIF response time needs to be much, much less than your safety process safety time because of the nature of things such as process lags or where the SIF set point is placed. How is this typically accomplished on a new process? Again, working with the process engineers, it's something that if you've got a contractor that is doing the design or is doing the if you've got computer modeling, if there's an Aspen model of the process, that's a great opportunity to make it part of your early engineering design and help set safety, your SIF trip points, as well as it could, depending on what you found as you're doing this analysis, doing it early enough, you may want to go back and change something about the process, physically go with an inherently safer design option in order to adjust these timelines as well.